Alright, so here we have question 3 of the November 2018 CAPS Mathematics Paper 1 question. So this question 3 is another question on sequence and series, similar to question 2. Here we just deal with the geometric, where in question 2 we had the arithmetic and the quadratic sequences. Alright, let's get into it. So geometric series has a constant ratio of r. So we know r equals a half, constant ratio of a half, and a sum to infinity of 6. So the sum to infinity is 6. Right, now what is the sum to infinity of a geometric sequence? Well, we know the sum to infinity of a geometric sequence is a over 1 minus r. Right, the first term divided by 1 minus the common ratio. But when is this true? Only when r is between -1 and 1. Okay, in this case a half, that is between -1 and 1, so we're good to go. Okay, let's see, what is the question? 3.1. 3.1 asks us to calculate the first term. So the first term is a. We can just use this formula. So sum to infinity we know is 6, and the formula is a over 1 minus r. So a over 1 minus, and r we know is a half. Alright, so 6 equals a over 1 minus a half is a half. So multiply both sides by a half. So 6 times a half is 3. Multiply this by a half, we're left with a. So there we go, that's our first term. Nice. Now 3.2. 3.2. Here we get asked to calculate the 8th term of the sequence, or of the series. So the 8th term, all we want to do is we want to find T8. Now before we get to that, let's write the equation, or the general formula for the nth term of a geometric series. So for geometric, we've got the first term multiplied by the common ratio n minus 1 times. Alright, so in our case, the nth term is the first term, which is 3, and our common ratio is a half, multiplied to the power n minus 1. Alright, so that's our nth term, and we need to find the 8th term, so we just replace n with 8. So T8 equals 3 times a half to the power 8 minus 1. So 8 minus 1 is 7. And then we just work this out. So 3 times a half to the power 7 is 1 over 128. And then that just simplifies to 3 over 128. So that is our 8th term. Oh, I see I did this one in pink again. Let's just convert everything into green so it just looks at least a little bit uniform. Now we can get on to blue for the next one, for 3.3. Okay, so 3.3, oh, that looks a bit ugly, some decimals. Okay, so 3.3, we're told that given that the sum, I'm just going to write this down again, the sum of all the terms from k equals 1 to k equals 20 of the formula 3 times 2 to the power 1 minus k. If that sum of this from the first to the 20th term equals 5,8125, 5,8125, then we have to find the value of n. Right, oh, that's not 20, 20 is the next term, sorry, this is just an n. My bad, that's just an n, so we need to solve for n. Now when we're working with the sigma notation, so sigma, that's just this is a Greek capital S, sigma. So all we want to do, that just means the sum of, right? So a couple of things. First thing I like to do is write the first 3 terms of this sequence. So substitute k equals 1, then k equals 2, then k equals 3 to find the first 3 terms. So for term 1, we'll substitute 1 into the place of k. So that'll be 3 times 2 to the power 1 minus 1, which will give us 3 times 2 to the power 0. Anything to the power 0 is 1, so that's just 3 times 1 is 3. So that's our first term. Our second term will have 3 times 2 to the power 1 minus 2. So that gives us 3 times 2 to the power -1. And our 2 to the power -1 is a half. 3 times a half is 3 over 2. And then for term 3, we'll get 3 times 2 to the power 1 minus 3. 1 minus 3. And that gives us 3 times, what is 2 to the power -2. And what is 2 to the power -2? That's 1 over 4, right? So 3 times 1 over 4 is 3 over 4. So these are the first 3 terms in our sequence. Now we can check if it's arithmetic, geometric, or quadratic. And I mean, this just looks like it's geometric, right? And it will be. Whenever there's like an exponent with a variable in, that'll be a geometric sequence. Okay, so what are we multiplying with each time? We're multiplying with a half each time, right? So 3 times a half is 3 over 2. 3 over 2 times a half is 3 over 4. Okay, so first, our first term is 3. Our constant ratio is a half. We're multiplying by a half each time. Alright, now we need to find, so this means the sum of. So we need to find the formula for the, or we need to know the formula for the sum of the first n terms of a geometric sequence. So let's write that in our general color again. So the Sn for a geometric sequence is a times r to the power n minus 1 over r minus 1. This could also swap around. You could have 1 minus r to the power n over 1 minus r. That's also fine. So you could have the 1 in the front and the r at the back for both of these. If you swap both of them around, that's still fine. It doesn't matter which one you use. You can always use the same one. Okay, so we're going to use that formula. So Sn equals, and we're just going to rewrite it again, a times r to the power n minus 1 over r minus 1. Alright, and now this n here, that's the number of terms. So to figure out the number of terms we need to use, we say this minus this plus 1. So to find this value here, we're going to say the top, that top value, minus the bottom value, plus 1. So in this case, it'll just be n, so this is perfectly fine. The only problem is when this is not a 1. So let's say, just as a quick side note, say we had something from k equals 3 to 10. Now, a lot of people immediately just go, okay, that's S7. But 7 is a problem because how many terms will there be? Well, there will be 10 minus 3 plus 1. So 7 plus 1, 8 terms. So we'll actually have to find S8. So just something to remember. Top minus the bottom plus 1. That's how many terms we're working out. Okay, nice. Let's get back to it. Okay, so we need to find Sn, and that n is fine. So a, our first term is 3. Let me rewrite that 3. 3. R, our common ratio is a half. So a half to the power n minus 1 all over a ratio minus 1. So half minus 1. Okay, and we get told that Sn is 5.8125. So we can actually write that in here. 5.8125. Great, and now we just need to solve for n from here. This can still get a little bit messy. So a half minus 1 is just negative a half. I'm just going to replace this. Half minus 1 is negative a half. And now we're going to multiply both sides by negative a half. So 5.8125 times negative a half, that's going to be 2.9 something. Let me just actually work this out. 5.8125 divided by negative a half. Times negative a half. My bad, I'm so sorry. Multiplied. Okay, negative 2.90625. Negative 2.90625 equals 3 half to the power n minus 1. Now we're going to divide both sides by 3. So we're going to say that divided by 3. So negative 0.96875. Negative 0.96875 equals a half to the power n minus 1. So now we take a 1 over, so we add 1 plus 1, 0.03125. 0.03125 equals a half to the power n. Great. So now you can do this on the calculator. You could probably turn this into a fraction, which is quite nice. I'm just going to use logs to practice a bit of logs. Right, so we can take log of both sides. So log of the left-hand side, 0.03125, equals log of the right-hand side, log of a half to the power n. Now why do we do this? Because if we're looking to solve an exponent, it's quite difficult to solve for an exponent unless we can get something simple like x to the power b equals, let's say, y to the power b. Now if the exponents are the same, then we know we can put the bases the same. Or if the bases were the same, then we can say therefore these two are equal. So if we can convert it into something nice like this, then we don't need logs. Otherwise we do. Okay, then why we do need logs is because this can go into the front. A very nice rule from logarithms, right? the n can go to the front. So I'm just going to do that in one step. I'm going to say, the n can go to the front. So I'll just get rid of those. Okay, n moves to the front, and now we can divide both sides by log half, then n is by itself. Okay, so let's just do that. Take this and move it over. Divide both sides by that. Great, so now we can just type that in the calculator. So n equals, let's type this in. So we've got log of that divided by log of a half, 0.5. And we get 5. So n equals 5. Nice. Now you could have also 0.03125, what is that? That is 1 over 32, right? So you could probably get that as 1 over 32. Alternate method, let's do this, would be that is 1 over 32 equals a half to the power n. Now 1 over 32 is the same as a half to the power of 5. And then we get a half to the power n. Bases are the same, therefore exponents are also equal. Great, so those are two methods to solve it. I think it was nice to look at both. Good. Now question 3.4, so the last one for question 3 here. Question 3.4. 3.4. I'm just going to rewrite this. So they say if we have this, write down the value of that in terms of p. So the first part says sigma, so the sum from k equals 1 up to 20 of 3 times 2 to the power 1 minus k. They tell us that's equal to p. Now we have to find this thing in terms of p. So that thing is the sum of from k equals 1 to 20 of 24 times 2 to the power negative k. Okay, so we can see there's some similarities. That gives us a clue that we want to see how they can be very similar. How can we make them look like each other, but maybe just a multiple of each other, right? That's usually the kind of thing we're looking for. So let's first just expand these exponents. So we're going to say the left-hand side. So this is still from k equals 1 to 20. And now we're going to say 3 is fine. But now 2 we can write as 2 to the power 1 times 2 to the power negative k. Right? This whole thing is still p equals p. But now 3 times 2 is 6. So we can just say 3 times 2 is 6, right? 6. Okay, so this is now a different, or just probably a slightly simpler way to write this value. Now let's look at what this one, if we can convert it to look something similar like to this. Okay, so what we can immediately see is 6 and the 24. That's the only difference, right? What's the difference between 6 and 24? Well, 24 is 4 times 6. So that's all we need to do here. We can rewrite this as from k equals 1 to 20. But now instead of 24, let's write it as 4 times 6 times 2 to the power negative k. Right, so everything is the same except for this 4. And what we can also do with sigma things, we can take this 4 to the outside. So we can write 4 over here. Okay, so now we see this is p. This is exactly the same, right? These two things are the same. So we have 4 times that thing. That thing is p, so our final answer is 4 times p. Right, 4 times this, which is the same as that, and that thing is p, so 4 times p. Right, that's in terms of p. Perfect. So that is our final answer. What you'll want to look for in these kinds of questions, if you come across them, see if you can simplify the two expressions that you have so they look like each other and one is maybe just a multiple of the other one. Alright, so that is it for question 3, and I'll see you again for question 4.